Hello and welcome to this video about resistors in series or in parallel. And we're going to look at two different kinds of circuits, series versus parallel, and how we're going to calculate potential difference, current, and resistance in these two different kinds of circuits. And then we'll look at the benefits of either series versus parallel circuits. Quick review. Remember what a simple circuit is. It has a source of potential difference and a load. The total current can be found by this equation. Potential difference equals current times resistance, V equals IR. Also, something to keep in mind, light bulb filaments themselves are resistors. So when we have a load here of a bulb, it also acts as a resistor. What happens if we add more than one resistor to the circuit? Well, resistors can be placed in the circuit in different ways. We have a parallel circuit which has multiple paths through which the current can travel, or we have a series circuit, and that provides a single path of conduction. So in a parallel circuit here, we have two or more components in the circuit. So in this case, there are three resistors, and you can see that they're connected across common points or junctions, and these junctions then provide separate conducting paths. You can see that the current could travel like this, or it could go over here, this way, or here. So those are, even if we got rid of this resistor, you can see this is still a parallel circuit because it has more than one path. Here we only have one pathway, so these resistors are connected in series. How do we calculate resistance, current, and potential difference for these two different kinds of circuits? There are different ideas involved when we talk about resistors in series versus parallel. Let's take a look at resistors in series first. So in this case, we have one path through which the current is traveling. And important concepts to remember are that for resistors in series, the potential difference across the battery is equal to the potential difference across the load. So we can say that the potential difference across the battery is going to be equal to each of the potential differences across the loads. Delta V1 right here represents the potential difference across R1 or resistor 1. The second point to make, for resistors in series, the equivalent resistance is something we're going to represent by capital R with a subscript EQ. It is going to equal the sum total of the individual resistances in that series. So resistance 1 plus resistance 2 plus resistance 3 plus however many we have, in this case there are only 3, the sum of those will equal the equivalent resistance. Another important point for resistors in series is that current in each resistor is the same. There's only one path, and that one path necessitates that the current across each one will remain the same. The total current depends on the equivalent resistance. So when we calculate the total current in this circuit, it's going to be equal to the potential difference across the battery divided by the equivalent resistance. Let's do a sample problem together. Let's say we have a 9-volt battery connected to 4 light bulbs, as shown in our diagram, and we have the resistance for each of those bulbs. Find the equivalent resistance for the circuit and find the current in the circuit. Well, I know that I can find the equivalent resistance by simply adding up all of the resistances that are in this series circuit. And when I add all of them up, I get an equivalent resistance of 18.0 ohms. Remember, we just learned that the total current is going to equal my potential difference divided by my equivalent resistance. I am told that it's a 9-volt battery, so my potential difference across that battery is 9 volts. I just found my equivalent resistance, and so my current is equal to 0.50 amps. Series circuits require all the elements to conduct. If you have one of these bulbs that burns out and current is no longer able to travel across the filament here, that filament is what is connecting, completing the circuit, then the entire thing, there is no current. You have then an open circuit and no current flows. So why would anyone arrange resistors in series? Seems like it's not a good idea. Well, there are some benefits for arranging resistors in series. Each added bulb decreases the current. So the bulb filaments don't have to withstand such high current. You can kind of have some cheap bulb filaments. Also, several lesser resistances could be used to add up to a single greater resistance. And it also might be important to require no current if any one of the component parts fails. That would be a safety issue. So there may be some device that you want to build that safety issue into. So now let's take a look at resistors in parallel. Resistors in parallel are going to be arranged like this. They have the multiple paths, and they are going to have the same potential difference across each of them. So that is something that is different from our resistors in series. Also, the sum of the currents in each resistor in parallel equals the current delivered by the battery. So the current delivered by the battery is going to equal to the current across each of the resistors in parallel. That's also different. And last, for resistors in parallel, equivalent resistance is going to be calculated in this way. 1 over the equivalent resistance is equal to 1 over resistance 1 plus 1 over resistance for resistor 2 plus 1 over, etc., for however many resistors there are in parallel. So let's do an example for resistors in parallel. This is actually the same problem. We have a 9-volt battery. We have the same resistances in each of those resistors. And we want to find the equivalent resistance for the circuit and find the current. Now remember, for resistors in parallel, this is the equation we're going to use to find the equivalent resistance. I can plug those values in. I can go ahead and solve for all these fractions, and those are going to be in ohms to the -1. I could think about it also as over an ohm, over 1 ohm. I can cross multiply at this point or multiply both sides by the equivalent resistance, and I get an answer of 0.917 ohms. Now I need to find the current. I know that the current in the circuit is going to be equal to the total potential difference, and I already am given that. It's 9.0 volts divided by the equivalent resistance. And I get 9.8 amps for the current in the circuit. Just to check for resistors connected in parallel, this equivalent resistance should be less than the smallest resistance, and it is, so this makes sense. There are obvious benefits to parallel circuits. They do not require all the elements in order to conduct electricity. You can see that if, say, this bulb burns out and current is no longer able to flow across that filament, it will not affect the other parts of this circuit. So household circuits are arranged in parallel. Obviously, it's really nice to know that if one part of that circuit it malfunctions, or if it's broken in some way so that it's an open circuit, all of the rest of the pieces of circuitry in your house are not going to stop working. But there are other benefits as well to parallel circuits. They allow for appliances to be standardized. Devices can operate at the same potential difference, and so we can have standard appliances. In the United States, happens to be 120 volts. Then if we have standard potential difference, appliances can be designed with resistances that are appropriate for their internal wiring. And so that allows us to have all kinds of really nice appliances because they are able to appropriately be designed. Another benefit for parallel circuits is that when the circuits are being designed, the equivalent resistance of several parallel circuits or several parallel resistors is less than the resistance of any individual resistor. And so really low equivalent resistance can be created by having a group of resistors that have higher resistances, and that may be desirable for whatever device you're designing. Advanced idea. The old holiday lights arranged in series were arranged so that if one of your light bulbs burned out, the entire string no longer worked. You didn't get light out of it. So that means it was an open circuit, current wasn't flowing. Well, they do make strings of lights that don't do that. How do they make those? How does that work? See if you can figure that out. And if you have other ideas, please feel free to research those ideas. And I look forward to seeing what you come up with, and we'll see you in class.